Good day, one and all. Welcome to the HESA e-library, also called the HESA Video Bank. This is part 3 of a series of videos that will talk about heat of neutralization, ionic strength, and solubility. So everything that you need to know about these concepts will be explained in this video. Right. So let's delve into it. Now, heat of neutralization. The topic itself gives away heat of neutralization. So most definitely we'll talk about neutralization reaction, which is a reaction between an acid and base to form salt and water, right? Now, when we come down a little bit, we are seeing energy changes always accompany chemical reactions. Now, the energy changes will come in two forms. It can either be exothermic, or it can be endothermic, right? So it can be exothermic or endothermic. Now, when we say it is exothermic, it means the reaction will lead to production of energy that will be released into the environment. So energy is produced in the reaction that's liberated into the surrounding, right? Good. Now, for such an exothermic reaction, always the enthalpy change is negative. It's negative. You get negative enthalpy change. And there's another type, which is endothermic. And in atomic reactions, what happens is that we absorb energy from the environment into the reacting medium, right? And then for such reaction, always the enthalpy change is positive, right? So we get a positive enthalpy change. Now, for the record, heat of neutralization or neutralization reactions are exothermic reactions. And so our value for enthalpy change is always a negative. Very important to note. Now, a typical way that you can see that the reaction, the neutralization reaction is exothermic is you can touch the container after adding the acid and base. You realize that the container becomes very hot. That shows that the reaction is releasing heat into the environment. Now, an example of acid-base reaction has been shown. This is a very common example. We have hydrochloric acid reacting with sodium hydroxide. Now we produce sodium chloride, water, and then heat. The heat here is showing that the reaction here produces heat, right? So that's the exothermic nature of this reaction. Very important to note. Now, this reaction can be broken down to the ionic form. Now, when we break it down to the ionic form, as has been illustrated here, we can cancel out the spectator ions, right? The spectator ions will be the ions that occur on both sides. So ions that occur freely on both sides. Sodium is here, sodium is here. We can cancel the sodium out. Chlorine is here, chlorine is here, right? Now, when you cancel, you have only these ions remaining. So we have H plus ion remaining here, and then OH minus ion remaining here, and then it will form this molecule, water, right? And so that will be the next reaction or the net change that occurred, right? The other ions that have been cancelled, we call them spectator ions because they have been repeated. So they are just accompanying the reaction. The actual reaction that occurs is this one. And so in neutralization reaction, the actual reaction that occurs is the reaction between the H plus and the OH minus ions to form water. Right? This is the actual reaction that occurs in neutralization reactions. Very simple. Very simple. Moving on. Right, so we are seeing that the heat of neutralization is the heat change when 1 mole of water is formed from the reaction between an acid and an alkaline. Heat, into bracket, negative enthalpy change is expressed in kilojoule per mole of water. Now, this definition is gotten from the net reaction that we saw here. Very simple. The next reaction is the formation of water. So we form water, and water is formed by reacting an acid and an alkaline, right? So the heat of neutralization will be the heat change to form 1 mole of water, as we can see from the equation here. As we can see from the equation here. Very simple. Very simple. Next up. Right. So we are saying heat of neutralization can be divided into different types. Example, we can have a strong acid reacting with a strong base or alkaline. We can have a weak acid reacting with a weak alkaline. We can have a strong acid reacting with a weak alkaline. We can have a strong base reacting with a weak acid. So we have different scenarios, right? Good. But there's an interesting observation that we have to note. Now, the statement in red says that heat of neutralization between strong acid with strong alkaline. We have been given different examples. The first example is hydrochloric acid reacting with sodium hydroxide, and then our heat of neutralization is negative 57.3. Now, when you have HCl with KOH, we are still getting negative 57.3. If you have nitric acid and then potassium hydroxide, we are getting negative 57.3. If we have nitric acid and sodium hydroxide, right, we are getting the same thing. And so you realize that from this, you realize that when a strong acid and a strong base meet, right, always the heat of neutralization is constant. Now, the reason is very simple. The strong acid and strong base, what is peculiar about them is that they undergo complete dissociation, right? And so when they undergo complete dissociation, the actual reaction that occurs is the reaction between the H plus ion and then the OH minus ions to form the water, right? So it is same for all the strong acid, strong base reaction. That is why the energy we are getting is constant, right? Now, mind you, this observation is not for all of them. When you go to a different scenario, you realize that it changes. It changes. So now we are saying heat of neutralization between weak acid and a strong alkaline. So the example, we have been given acetic acid with sodium hydroxide. Now we form sodium acetate and water. The heat of neutralization now has become negative 55. So that's a significant decrease. It's a significant decrease. Now, what is bringing about the significant decrease? Let's look at the next observation. We have HCN plus KOH, and then you realize that the heat of neutralization here is negative 12. So it has a drastic decrease, right? Now, the idea or the problem here is coming from the weak acids. Now, the idea is that the weak acids do not dissociate completely. They dissociate partially to produce only few ions. Now, for the reaction to undergo complete reaction, it has to fully dissociate the weak acid. And that dissociation requires an extra energy, right? And so the reaction absorbs an extra energy before the product can be formed completely to release the energy, right? So the net energy becomes smaller. That is the idea, right? Good. So unlike the weak acids, the strong acids, which dissociate completely, the weak acids dissociate partially. Now, because of their partial dissociation, they have to absorb extra energy to overcome their intermolecular bonds, right? Overcome their intermolecular bonds to now fully dissociate. Before now, they come and react completely to give us our product. So that is why the heat of neutralization here has reduced. So if we are reading, we are saying that weak acids only ionize partially in water. Only small amount of hydrogen ions is produced. Most of the molecules of weak acid still exist as a molecule. Therefore, some heat energy is used to overcome the molecular bond in the acid, right? So that it can be ionized in water. Thus, this process causes the heat of neutralization to be less than 57 kilojoule per mole. That is that for that. That is that for that. Now we are seeing heat of neutralization of weak acids with sodium hydroxide at 25 degrees. So these are standardized ones that we have checked. You realize that if we do against acetic acid, as we observe in the other table, we get 55. Now it takes 2.09 heat, right, to fully dissociate the acetic acid. So that's the heat of dissociation. If it's formic acid, you get negative 56.06, and then you need 1.26 of energy to fully dissociate formic acid, right? If it's hydrocyanic acid, we need about 45.19 kilojoule per mole before we can completely dissociate, right? This one, that has drastically reduced the heat of neutralization. And so the whole idea is that if we have either a weak acid or a weak base coming in play, some of the energy would be used to fully dissociate that weak acid or weak base, and hence the overall heat of neutralization decreases. That is that for that. Moving on. So, heat of neutralization. The heat of neutralization of any strong acid, example HCl, and HCl by any strong base like sodium hydroxide is same. Why? So we have talked about that. We are saying strong acid and strong base fully dissociate in solution. No energy is required for their dissolution. So regardless of what acid strong acid or what strong base, the common process is taking place, which is the reaction between the H plus and the OH minus ions to form water. So always you get the same value of heat of neutralization, right? But then if we introduce either a weak acid or a weak base, it changes because for complete neutralization to take place, the weak acid or weak base must first fully dissociate. And this requires energy. And so in summary, we are saying that the overall change is as a result of two reactions. The dissociation into ions, which is endothermic. The weak acid or weak base has to now consume energy to dissociate. So that's endothermic, right? Before the neutralization process will occur, which would be the exothermic reaction. Now, some calculations. Heat of neutralization. We are saying energy released by the reaction is equal to energy absorbed by the solution. Now, the first term that we are supposed to talk about is specific heat capacity. Now, this definition is a very lazy definition. It is coming from the mathematical formula. Very simple. So it's defined as the quantity of heat transferred, right? The quantity of heat is denoted by K divided by the mass of the substance times the change in temperature. That's exactly what has been stated mathematically here. CS is equal to K over mass into brackets, final temperature minus initial temperature. Very simple. Right now, if we do change of subject rearrangement, we can now make Q the subject. That's the quantity of heat transferred. And it will be equal to the specific heat capacity times the mass times the change in temperature. Now, this is a formula we have to keep because we will be using this formula in almost every calculation that we do. Very important. Now, in order to get the enthalpy change, right, we have to now divide the heat transferred by the number of moles or the amount of substance, right? The amount of substance in moles to get the enthalpy change. Now, mind you, heat of neutralization reactions are always exothermic reactions, and so the energy you get should always be negative. The negative might not be apparent from the calculation, but from theory, you know that heat of neutralization is endothermic process. And so always you make sure your enthalpy change is a negative value. Thank you very much. Now, the concept of measuring temperature changes, right? The science and the device we use, we call the whole concept calorimetry, right? The instrument we use itself is called a calorimeter, right? So a calorimeter is like a container which can host a reaction mechanism and then enable us to check the temperature rise and fall, right? The temperature difference between the starting and the end, right? So that is just calorimeter and calorimetry. They have given us two examples or two types of calorimeter. We are not supposed to go into the types in this one, but they gave us a coffee cup calorimeter and a bomb calorimeter. Now, the classical difference between these two, right? The coffee cup is used to measure enthalpy change. Usually the bomb calorimeter is used to measure internal energy. So that's one of the major differences that you can get. And then reaction that require constant pressure, right? We use the coffee cup. So that is what has been written down here. And then for the bomb calorimeter, we are looking at constant volume, right? Constant volume. So that's for that. Now this is how we set up the coffee cup. I've already said that the coffee cup is what we use to measure enthalpy change. Now, we have to take note of these numbers because we will use them to solve questions on the next slide. So, typical experiments using a coffee cup calorimeter. So, we are saying 50 mL of 1.00 molar HCl would be placed in a coffee cup calorimeter and carefully measured its temperature to be 25.5. To this would be added 50 mL of 1.0 sodium hydroxide solution whose temperature is also 25.5. The mixture is quickly stirred and the change temperature noted, right? So this is how the experimental setup is done. So this is a graph showing how the energy will, the temperature will rise. So where the arrow is now is the starting, and then it will move here. At the peak here is where the reaction is complete. So we check the difference here, the difference between the initial temperature and the final temperature to get our temperature change, which we'll use in our calculation. Now, for the purpose of calculation, we are saying that assuming the temperature of the mixture rose to 32.4, what is the heat of neutralization? So I've already said that this is the formula that we'll use to find the Q is equal to MC change in T, right? The Q is the heat transferred, the M is the mass, the C is the specific heat capacity, and then the change in T is change in temperature. Very simple. Now we have been given more assumption on this slide. We are saying assume that the solution formed after the reaction is water, which is of course water. When you add sodium hydroxide and then hydrochloric acid, you form salt and water. Because we cancel out the spectator ion from the ionic equation, we get the actual reaction occurring being forming water, right? So that is what we look at, and that is what we use in our calculation. Now they have given us the specific heat capacity, which is 4.1984 joules per gram per degree Celsius. Now the density of water is 1.00 gram per mil. Very simple. Now we are asked to calculate the heat of neutralization. So we first get our Q, and then if we need the enthalpy change, then we'll divide the Q by the amount of substance to get our enthalpy change. It's a very simple calculation. Let's go through. Now, per the formula, we need the mass, but we don't have the mass from the question. But what we have is they have given us the volume. The volume, we added 50 mils of HCl to 50 mils of sodium hydroxide. And so the total volume we have now is 100 mil. That is where this 100 is coming from. The 100 is not stated in the question. But if you read the question and realize that it was 50 of HCl, 50 of NaOH, you get 100 mil. And then when the reaction is complete, we form water. So at the end of the reaction, the only liquid in the medium is water, right? And the density of water has been given. We all understand that density is equal to mass over volume. When you do the change of subjects, mass will be equal to volume times density. And then per the calculation here, we get 100 grams of the solution, right? Good. Now, after getting this one, we have to now find the change in temperature, because the C has been given in the question. The C has been directly given in the question, so we just have to find the change in temperature. Now, the initial temperature was 25.5 from the question. Final temperature was 32.4. So it's just a subtraction, right? We do a subtraction, we get 6.9 degrees Celsius. We come and put the figures in this equation, and that will give us 2.9 times 10 raised to the power 3 joules, right? So this is the heat transferred. Now, in order to calculate our enthalpy change, we have to divide by the number of moles. Mind you, per theory, when a strong acid and a strong base react, right, we get a constant value around negative 57.3. And so if you do this calculation between strong acid and strong base, and you get something which is not close to 57.3, you are wrong. It's not negotiable. You have to get something around 57.3 kilojoule per mole. So if you get something which is too high or too low, you are wrong, because this is something is a fact, right? It's a fact that will work around. So that's an easy trick for you to know whether you actually did the right thing, right? So we use it to check whether this calculation is correct. Now, we have to check the number of moles of HCl or NaOH used. Now, the question has never given us the reaction mechanism, the equation of the reaction, but let me write it here for understanding sake. So this is the overall reaction. Sodium hydroxide plus HCl reacting to form sodium chloride and water, right? Now, in this reaction, 1 mole of this reacts to 1 mole of this. But the actual reaction, how many moles of sodium hydroxide was there? From the question, we know or we understand that the concentration of sodium hydroxide was 1 molar. 1 molar is the same as 1 mole per dm cube. So 1 mole per dm cube, right? Yes. Now, 1 mole per dm cube, if you want to explain this term, it means 1,000 mil. 1 dm cube is 1,000 milliliters, right? Dm cube is the same as liters, right? So you know 1,000 milliliters is equal to 1 liter. So if it shows that for the sodium hydroxide, 1,000 mils of sodium hydroxide contains 1 mole of the sodium hydroxide solid. This is the meaning of the concentration that we have here, the 1 molar or 1 mole per dm cube. But then in the solution or in the reaction, we introduce just 50 ml. So if 1,000 ml contains 1 mole, then 50 ml will contain what? So it's just a matter of cross multiplication. We have 50 times 1 over 1,000, and that will give me 0.05. So this will become the amount of substance of sodium hydroxide. And per the reaction mechanism, if 1 mole of this reacts to 1 mole of this, it means if this is 0.05, this one is also 0.05. At this juncture, the only thing we have to do is that we have to calculate for the enthalpy change by just substituting these values in the equation. Now we have the Q already. The Q is 2.9 times 10 raised to the power 3 joules, right? And the N from this one is 0.05 moles, right? Good. So if you do this chemistries, the thing has been solved. So let me just go through. You get 58, negative 58. Right, so the solution has been given here. When you do your division at this level, you get negative 5.8 times 10 raised to the power 4, right, which is the same as 58, which is the same as 58,000, right? So this 58,000, right? And then if you want to convert it to the appropriate unit, which is kilojoule per mole, you will get 58 kilojoule per mole. The negative is coming in not because of any calculation. It is because we understand that heat of neutralization is always negative, right? It's an exothermic reaction, right? So that is where that is coming from. So we have concluded. Now you realize that I told you that the value, the standard value is 57.3, negative 57.3. So if you get 58, you know you are right because you are around negative 7.3. But assuming I got 75, I mean, there should be something wrong or there should be another explanation in science, right? But 58 is very close to negative 7.3. And so I can be confident about it. Now, there's another question here. Without thinking, usually you don't have to think a lot. Without thinking, the solution is not here. I'll solve the question. But it is sodium hydroxide reacting with HCl. The standard enthalpy change, the enthalpy change would be around negative 57.3. So whilst I'm solving, I have it at the back of my head that my solution should be around negative 7.3. So let's go through this one. Now we are saying that in a coffee cup calorimeter, 50.0 mils of 1 molar NaOH and 50 ml of 1 molar HCl are both mixed. Both solutions are originally 23 degrees Celsius. After the reaction, the temperature is 30 degrees Celsius, assuming all solutions have a density of 1.0 gram per mil and a specific heat capacity of 4.18 joule per degree Celsius per gram. What is the enthalpy change for the neutralization of HCl by NaOH? Assume that no heat is lost to the surrounding or to the calorimeter. Very simple question, easy peasy, lemon squeeze. Let's do it. Good. Now, the first formula without thinking is this one. Q is equal to, so Q is equal to MC, change in temperature. Now, what is the mass? We don't have the mass, but then they have given us a density of 1.0, and then they have given us a volume. The volume would be 50 plus 50, so the volume will be 100 mils. 100 mils, right? 100 mils. Now, we understand that density is equal to mass over volume, right? And then the mass, by doing changes, will become density times volume. And so we have mass being equal to 100 times 1. The 100 is the volume, the 1 is the density, and that will give me 100 grams, right? 100 grams, so that is that for that. Now, for the temperature change, we have the final temperature minus the initial temperature. The final temperature is 30 degrees. We have 30 minus the initial, what is 23? So that will give me 7. That will give me 7, right? 7 degrees Celsius. That's all. Now they have given us a specific heat capacity, so we can just calculate for the Q, which is the heat transferred. It will be 100 times 4.18 times the change in, which is 7. Let me punch that quickly on my calculator. 418 multiplied by 7. So that gives me Q being equal to 2926 joules, right? So this is the heat transfer. Now, for me to get my enthalpy change, right? Enthalpy change, it has to be Q over N. Now, we don't have the N, right? But we can use any of them. The reaction is still the same. It's like this. Sodium hydroxide plus HCl reacting to form sodium chloride plus water. The OR is coming from my British accent. Good. So 1 mole of this reacting 1 mole of this. Now we have to actually know the number of moles which came from up there, right? We have 50 moles of 1 molar. Now 1 molar means 1,000 mils of the solution contain 1 mole. So 50 will contain what? 50 will contain what? So it's the same calculation we did over there. Cross multiplication, we get 50 times 1 all over 1,000. And that gives me 0.05, right? So if I want to finalize my calculation, the enthalpy change will be K, which is 2926 divided by 0.05 mole. So that will give me the enthalpy change would be 58520 joules, right? Now, for it to be very appropriate, I have to convert it to kilojoule per mole, right? So this is joule per mole, joule per mole. I have to convert to kilojoule per mole. So I move the 0.3, 1, 2, 3. Kilo is divided by 1,000, right? So I'll come and get the enthalpy change being equal to 58.5 kilojoule per mole. That is that for that. Very simple calculation. You can do that without thinking. Good. Next up. Chemical properties on ionic solutions. So we are saying that in all of equilibria that have been discussed so far, we have assumed that the equilibria occurs in ideal solutions. But then, solutions of electrolytes, a large number of oppositely charged ions influence one another through interionic attractive forces. Although this interference is negligible in dilute solution, it becomes appreciable at moderate concentration. In solutions of weak electrolytes, regardless of concentration, the number of ions is small and the interionic attraction correspondingly insignificant. Now, this is where it gets interesting. Strong electrolytes may be completely ionized, yet incompletely dissociated into free ions due to electrostatic attraction between ions and ion association into groups. Now, the whole English that I've read is first of all acknowledging that even though strong electrolytes fully dissociate, right, fully ionize. Now, even though they fully ionize the solution, they don't fully dissociate. And so if I'm supposed to illustrate something like this, if I have a solution containing sodium plus and then Cl minus, now the sodium chloride will fully ionize in solution, but this is still positive and negative, and always there's an attraction between positive and negative. So even though it is completely ionized, but then there's still some attraction, especially if the concentration is high. It is very insignificant if it's infinitely diluted. If it's infinitely diluted, but if we have a significant concentration or moderate concentration, this interaction is significant. And so all the calculations that we have done, where we just assume that sodium chloride will undergo full dissociation, so we just use their concentration, we are wrong. That is only true for ideal solutions. And the ideal solution will occur when we have very dilute concentrations, or when we talk about weak electrolytes. And so now we are introducing another concept where we call it real solutions. In real solution, we factor in the attractive forces. We factor in the attractive forces because we understand that even though there's complete ionization, complete dissociation is not always assured. So that is what we are talking about here. Let's go on and read more about this concept. Now we are saying that when ion concentration become high enough so that ion the interaction affects solution equilibria. Equilibria are affected not only when the concentration of ion involved in the equilibrium become high, but also when concentration of spectator ion becomes high. Now, what we are talking about, this is a very interesting point, is an attraction between a positive and a negative charge, electrostatic attraction. And so whether the ions are directly involved in the equilibria or they are just random ions in the solution, it will still have a part to play in this attraction. And so we are saying that equilibria is affected by both the ions in the equilibria, but that's not that alone. Even the ions which are spectator ions influence. So for better understanding, let's do this illustration. Now, if I'm talking about sodium chloride, right? Now, the effects will not be just the attraction between the sodium chloride, but if there's, let's say, calcium ions in the medium, the calcium ion can also affect this chlorine because of the opposite charges they have. So that is what we are talking about. That even the spectator ions can have an effect on the equilibrium, even though they are not directly involved in the equilibrium reaction. Very important to note. Very interesting concept coming up. Very interesting times ahead. Good. So I think spectator ions are not involved directly in equilibrium, but they affect the environment of the ion that are part of the equilibrium. Hydration. Now, we are saying that ions do not act as independent particles in solution. They are surrounded by a shell of solvent molecules. And so this is the behavior of water. Water is made of oxygen and 2 moles of what? 2 atoms of hydrogen. Now, the oxygen here is highly electronegative. So always it pulls or it polarizes the bond. It pulls the shared paired electron towards itself to get a partial negative, and then the hydrogens become partial positive. So this is the behavior. Now, if there's a metal in the solution, the metal is coordinated, or the metal binds to the oxygen because the oxygen is partially negative and the metal is partially positive. If there's an anion, the anion binds to the hydrogen because the hydrogen is partially positive and the anion is partially is negative. Right? So these are electrostatic attractions that occur in solution. So ions do not move independently. They are shielded or they are surrounded by solvent molecule. Now, another example has been shown here. We have calcium and sulfate ions being circled by water molecules. So the calcium is positively charged. You see that oxygen molecules are around it because the oxygen has partial negative charge. The sulfate is negatively charged. You see hydrogen ions around it. That is that for that. Now, the hydration of calcium and sulfate ion to induce shielding, which affects the ability of calcium and sulfate to meet and react. So what we are seeing that the hydration, now the hydration brings a lot of some sort of shielding, because when the calcium and the sulfate meet, they will form calcium sulfate, we can precipitate out. So the hydration is a form of shielding these ions and preventing them from meeting so that they don't precipitate out, right? So that's a very simple concept for us to take note of. Now, if other ions like sodium, so this is the influence of spectator ions that we are talking about. If other ions like sodium and chloride are added to the calcium sulfate solution, they are attracted to the ion of opposite charge. So you realize that now the shielding is not being done by just the water molecule. The chlorine from the sodium chloride is also shielding the calcium. So it increases the shielding here. Now, the sodium ion from the sodium chloride is also shielding the sulfate here, right? And so it's increasing the shielding. Now, this one has a classical effect in the dissolution of calcium sulfate. And so you realize that when calcium sulfate dissolves, let's say if we put 10 grams of calcium sulfate in water and just 5 grams has dissolved, when you add sodium chloride, right? Sometimes you realize that an extra 3 grams can dissolve. That is because the sodium chloride, even though it's not involved, there's no common ion, it's not involved in the equilibrium, right? It increases the shielding of the calcium and the sulfate ion, right? Further allowing more of them to dissociate. It shields them. It shields them, further allowing more of them to dissociate. So that is what we are looking at. There are Englishes around here. Let me read the English. So they are saying that the added ion effectively increase the amount of electrostatic shielding, that's decreasing the ability of the calcium and the sulfate ions to interact. Therefore, gypsum, which is calcium sulfate dihydrate, will appear more soluble in seawater than in fresh water, right? Good. Now, why is it appearing more soluble in seawater? Because the seawater would have spectator ion that will increase the shielding of the calcium ion and the sulfate ions, right? When you increase the shielding of the calcium ion and the sulfate ions, it will allow more of what the salt to dissolve because it is reducing the interaction of these ions, making them blind away from each other. Now we are seeing in such solutions, the equilibrium constants are expressed in terms of this effective concentration, which is normally called the activity, which is the concentration of available, which is the concentration available for reaction. Now, activity is equal to effective concentration. At this point, this is the right point for you to note that in any question, in real life setting or in any real life scenario, if you are given the concentration and you are given the activity, you have to use the activity. You don't use the concentration because the activity tells you the effective concentration which is available for the reaction to proceed. So we don't use the concentration, we use the activity. Ionic atmosphere. Ionic atmosphere. Ionic atmosphere. Now we are seeing cations are surrounded by anions, anions are surrounded by cations, right? Now let's use these pictures to illustrate. So this is a cation. Now the cation would be covered or shielded by anion. So the plus here is shielded by a negative, partially negative species. Now the negative here is being shielded by a partially positive species. Now, if that happens, the effective charge is decreased. So if let's say this is +2, right? That is the effective charge, the force coming here. Now, this one will reduce it. So by net, it can be +1 or +0.5 or something, right? Yeah, so that's what we are talking about. We are saying shows the ion and decrease the attraction. Now, because the effective charge is decreased because of the shielding here, because the effective charge is decreased, the attraction between these ions also decreased drastically. That is what we are talking about here. Very important to note. Now we are saying the net charge of ionic atmosphere is less than that of the ion, right? Obviously because of the shielding. But then it has also added that ions constantly moving in and out of ionic atmosphere. So this is a picture. You realize that each ion now sees less of the other because of what the ionic environment or the ionic atmosphere surrounding the ion. Now we talk about a very important term. This important term is called ionic strength. Now the ionic strength is important because it can help us calculate the activity of a solution, which is the effective concentration, right? Now it can help us by, okay, we'll talk about that subsequently. So let me focus on ionic strength. So we are saying that this effect of the ionic environment within a solution is known as the ionic strength, right? Now the ionic strength is the measure of the inter-ionic forces in the solution of strong electrolytes. That is not a definition that's I like. The definition I like is this one, this definition. The ionic strength is the measure of the total concentration of ions in a solution. So every single ion, the total concentration of ions in the solution is what we call the ionic strength. And that's my favorite definition of ionic strength. Now, when we are calculating the ionic strength, the highly charged ions are more counted. But then the sum extends to all ions. That is why I like the total concentration of ions, because every ion is considered. Whether it is a main ion or it's a spectator ion, it is considered. But then the highly charged ones, because the highly charged ions introduce greater shielding. Now, the formula for finding ionic strength, very simple. So we have half of the summation of the concentration of the ion times the charge of the ion squared. So this is the formula, the condensed formula, and this is the formula we use, right? Now, if you want to expand the formula, is half into bracket the concentration of the first ion multiplied by the charge of the first ion squared plus the concentration of the second ion multiplied by the charge of the second ion squared. It goes like that. So we add, so we get to the last ion, and then when we finally evaluate to get the answer. So that is that for that. That is that for that. Now we are saying that ionic strength is used to measure, it's used in the measurement of ionic activity coefficient using the Debye-Hackles equation. This was what I was talking about. That's the only reason why we are studying ionic strength is because it can help us to measure the activity of a solution, which stands for the effective concentration. And how it will do that is that it helps us to now determine the ionic activity coefficient. And the ionic activity coefficient will go ahead to help us to find the activity. So the ionic strength will not exactly directly help us to find activity. No, it would first of all help us to find what? The ionic activity coefficient. Now, what will help us do that is the Debye-Hackles equation. We'll talk about that. We'll talk about it, but let's do some calculation. Let's find the ionic strength. The first question says, calculate the ionic strength of 0.01 molar sodium sulfate. Let's do that. Sodium sulfate. Good. So now the first thing is that you write the equation for sodium sulfate dissociated, right? Yes, complete dissociation, but don't be confused, right? So complete dissociation, sodium sulfate, complete dissociate. I'll get 2 moles of sodium ions plus sulfate ions, right? Good. Now we have 0.01 molar here. This place will become 0.02. 0.02 because of the 2 here, and this will still be 0.01. The idea is that 1 mole of this gives 2 moles of this and 1 mole of that, right? So you be very proportionate when you are considering that. Now the equation, the ionic strength is equal to half of the sigma, the summation of into bracket CI ZI squared. So if I'm looking at that, then I have the ionic strength being equal to now half into a square bracket, a very big bracket. Now we have brackets, the concentration of this, which is 0.02 multiplied by the charge, which is plus 1 squared, plus now the concentration of this, which is 0.01 multiplied by minus 2. The charge here is minus 2 squared, right? The charge of sulfate is minus 2. And so if you simplify this side, you get the 1 squared is 1 times the 0.02 will be 0.02 plus this, the 2 squared, negative 2 squared is 4 times this will give 0.04. Now when you add these two, you get 0.06, right? Divided by 2, that is the half here. That will give you 0.03. So my answer here will be 0.03. The question has been solved at the back. Easy peasy, lemon squeezy. Right. Now the next one, same thing. Let me draw the reaction. It's still sodium sulfate. So yes, now it's sodium sulfate and then potassium nitrate. So let's write the equation for both of them. The KNO3 would give me K plus NO3 minus, right? Good. Now 1 mole of this reacts to 1 mole of this. So if I have 0.01, this is 0.01, this is 0.01, right? Good. Now for the sodium sulfate, right, it will be no different from the one I wrote up here. I'll have Na2SO4 reacting to give you 2 moles of Na plus SO4 2 minus. Now here I'll have 0.01. This side would be 0.02, and then this side would be 0.01. Right, good. Now, for me to get the total ionic strength, I would have half into brackets. So half into brackets. The first one, this first species is 0.02 multiplying plus 1 squared plus the sulfate. The sulfate is 0.01 minus 2 squared plus the KNO3. This one, the K plus is 0.01 into bracket plus 1 squared plus the NO3 minus is 0.01 into bracket minus 1 squared, right? Bracket close. Now this one would give me 0.02. This one will give me 0.04. This one will give me 0.01. This one will give me 0.01. So this is 0.06. This is 0.07, 0.08. So I'll get 0.08, right? Then divided by the half here, I'll get multiply by the half, I'll get 0.04. So my answer will be 0.04. Very simple. You can do that without thinking. And the answer has been laid out at the background. Good. Good. Now we have more work to try. Very simple. The KCl, it will be KCl reacting to form 1 mole of K plus, and then 1 mole of Cl minus, right? This is what we'll get. We can try. The barium sulfate, same thing. The charges, this is 2 plus and this is 2 minus. So that is what has been shown here, right? Very simple. And then the sodium sulfate has been calculated on the format slide, the same question. Get this. Now from this, we can get some tricks. So the tricks are what we have to look at this point. Now, if the charges is like plus 1 minus 1, if it's 1:1, right? Now, the ionic strength is the same as the concentration. That is what we can observe from here. Now, if it's 2:2, like this one, barium is plus 2, and this is minus 2. If it's 2:2, then the ionic strength is 4 times the concentration. Now, if it's 1:2, because sodium here is plus 1, sulfate is minus 2. So if it's 1:2, if the charge is the ratio is 1:2, then the ionic strength is 3 times the concentration. So these are the things. It has been listed down here for us to consume. Very simple. So if you have some of these facts in your head, before you calculate, you know your answer, right? Now, there's another question for us to calculate the ionic strength of seawater. Now, the question is very simple. We just follow the rules. The charges have been given here. The concentration have been given here. So if I'm supposed to calculate for seawater and probably leave Nick for us to do. Now, the seawater, the ionic strength will be equal to half into brackets. Now, the concentration 0.49 times 1 raised to the power 2, that's for sodium, plus magnesium is 0.053 times 2 raised to the power 2. Now, the truth is always squared. So whether it's positive or negative, when you square the number, it becomes positive. So you can just take the numbers and square them, right? If it's -2 and you square, you get +4. If it's -1 and you square, you get +1. If it's +2, so because it's squared, we square the charge. We can just take the value or the magnitude and then do the calculation with. So that's what I'm doing here. It's not wrong. For the calcium, I have 0.01. The charge is +2, so times 2 squared. And for the calcium, sorry, for the potassium, I have 0.01 times 1 squared plus, now for the chlorine, I have 0.57 times 1 squared plus the sulfate, I have 0.028 times 2 squared. And then the carbonate ion, I have 0.002 times -1, that is 1 squared. Now, if you punch all of this in the calculator, you're supposed to get the answer that you have gotten here. Very simple. You're supposed to get the answer that you have gotten here. Very simple, right? So that is that for the lake. Now the lake, you do the same thing. So it becomes the concentration of the ions multiplied by the charge square of each of them. Now we are saying that from this calculation, you realize that the ionic strength of seawater is about 500 times that of lake water. We have a question to solve here. I'll solve this question with us. Now the solution has been presented here, but you realize that the solution is not exhaustive. So then I have to come in with the exhaustion. Now the question reads, a buffer contains 0.3 moles of K2 HPO4 and 0.1 mole of KH2PO4 per liter of solution. Now, once they say per liter of solution, they are talking about concentration. In effect, they are talking about 0.3 per liter. That's 0.3 mole per dmq or 0.3 molar. But once they say 0.1 per liter, they are talking about 0.1 per dmq, which is the same as 0.1 molar. So they have given us the concentration, right? So I don't have to worry about those ones. Now, for us to understand the reason why we arrived at it, we have to first of all dissociate the potassium hydrogens phosphates like this, right? So we have this. Now I'll get K plus 2 moles of K plus HPO4 2 minus. So this, right? Now I have 0.3 here. This one will be 0.6 because it gives me 2 moles of this, and then this 0.3. And so for this one, if I'm doing the calculation, I would have half into brackets. 0.3 times 2, that's a 0.6 here, times 1, which is the charge, squared, plus 0.3, this is 0.3 here, then the charge is negative 2 squared. Now, if I look at the second sort here, I have K. Now, when you split, you get K plus H2PO4 minus, right? Now, this is 0.1 mole, this will be 0.1 mole, that's 0.1 mole. 1 mole of this reacts to form 1 mole of this. That reacts to form 1 mole of this, right? So that is what we have here. So we have 0.1 times 1 raised to the power 2. 0.1 coming from here. 0.1 coming from here, and then 1 coming from here. The next one is still 0.1, and then the charge is -1 coming from here. Now, if you punch all of this in your calculator, you will get 1.0 mole per dmq as your ionic strength. So that is that about ionic strength. Now, there's this last question that we have to look at before we go to the application of ionic strength. The last concept here, which the last question on the ionic strength, is the effect of ionic strength on solubility. Now, equilibria involving ionic compounds are affected by the presence of all ionic compounds in the solution. So they have given us that this is mercury 2 iodate. We call it the mercuric iodate. Now it dissolves to give you mercury and then iodate ions. Now we say when you place this in pure water, the solubility is just this. You get 6.9 times 10 raised to the power -7 dissolving. However, when you put 0.05 of KNO3 in it, now the solubility will increase significantly, right? Now, the first thing we have to all agree on is that this number here is bigger than this number, even though this is 6.9, but it's times 10 raised to the power -7. This times 10 raised to the power -6. So this is the bigger number. This is bigger. That's one thing that we all have to agree on. When we are done agreeing on that, then the only difference between the two is that they have added a salt here, right? You have added the salt here. So the salt is the one which is increasing. We can make an assumption that the salt is the one which is increasing the solubility in the second case. Now, how is it doing that? The ionic environment, even though the equilibrium here, the salt is not part. There's no K, there's no NO3 here, right? The ionic environment will still affect this. And so what will happen here is that the K, which is positive K plus ion, will come and shield this. Now, when it shields this, the nitrate ions will also come and shield this. The shielding here would make these ones move further apart, see themselves less, and then further dissociate. So that will cause more of this to dissociate. That will cause more of this to dissociate because of the increased shielding introduced by the environment, which is the potassium ion introduction and then the nitrate ion introduction. So that's the idea. In summary, when the KNO3 is added, it will dissolve completely to form K plus ion. So it will form K plus ion. The KNO3 will form K plus ion plus NO3 minus ion. And these ions would increase the shielding of the mercuric ion, Mercury2 ion, and then the iodine ion. Further pulling them apart, that will cause more of the undissociated mercuric iodate to dissociate. That is what has resulted in the increased solubility of mercuric iodate. And that is why most sparingly soluble salts might be more soluble in seawater than in lake water or in fresh water. That is because of the increased ionic environment, the ionic strength, which will increase the shielding of the ion, causing more of the undissociated salts to dissociate. That is that for that. Now, activity. I'm saying that activity is the effective concentration, right? Now we can calculate the activity by multiplying the concentration by the activity coefficient, right? The activity coefficient. Then the activity coefficient here will serve as a correction factor, right? And then it will tell us how the concentration deviates from the ideal concentration, because this concentration we state here are the ideal solutions, right? Now, in non-ideal solution, it is the activity coefficient that will tell us by how much the solution is deviating from its ideal property. So if the solution is ideal, the activity coefficient is 1. Now, when I put 1 here, it means the activity is the same as the concentration, 1, right? Now, if I am moving away from 9 to 0.9, it means it is deviating. If I'm moving away to 0.2, it means the deviation is very large. But then here, the deviation is very small. So that is how the deviation goes, right? That is how the deviation goes. Now, if you are looking at real equilibrium constants, right? Now, equilibrium constant is usually the product of the concentration of the products, the product of the concentration of the product raised to the appropriate stoichiometric ratios divided by the product of the concentration of the reactants raised to the appropriate stoichiometric ratios, right? Yes. But then these concentrations that we use under these conditions are ideal concentrations, right? But in real solution, we have to multiply all of the concentration by the activity coefficient so that we can get a real equilibrium constant. A real equilibrium constant. Activity and activity coefficient. Now, I've explained all these, so I'll just go over them. We are saying that in any real solution, interactions occur between the components which reduce the effective concentration of the solution. The activity is a way of describing the effective concentration. The ratio of the activity to the concentration is called the activity coefficient, right? So very simple maths. This is a very simple maths. Let me just narrate it. The activity is equal to concentration multiplied by the activity coefficient. Now, if I do change of subject, I can divide this by the concentration, divide this by concentration, so that I'll get the coefficient is equal to the activity by the concentration. So that's what they have said, that the ratio of the activity to the concentration is called the activity coefficient. Some of these things we don't have to chew. Now, if the solution is ideal, the activity is equal to, and the activity coefficient is equal to 1, right? Yes. When brags are solved, the ionized solution, the activity of each ion in the solution is the product of the activity coefficient and the molar concentration. So if we want to find the activity, which is the effective concentration, always what we do is that we multiply the concentration by the activity coefficient. Very simple. Right. Now, equilibria in electrolytes. The same thing. We are talking about equilibrium constant and activity. Real equilibrium constant using activity coefficient. Activity is always less than or equal to 1. It is 1 when it's ideal. It is less than 1 when it's real. That is when the deviation starts, right? Now, activity coefficient measures the deviation from ideal behavior. We talked about that. If the activity coefficient is 1, the behavior is ideal. and typical form of equilibrium constant is used. The typical one, right? This is the typical form of equilibrium constant. This one is the typical form of equilibrium constant, right? Yes. Now, activity coefficient depends on the ionic strength. So before we started the discussion on ionic strength, I said that ionic strength is important. We have to learn about ionic strength because it can help us calculate the activity coefficient, which can also help us calculate the activity, which stands for the effective concentration. So now it's coming to bear. Right now, activity coefficient decrease with increasing ionic strength, right? It decreases with increasing ionic strength. Approach 1 at lower ionic strength. So when the ionic strength is increasing, right, now the activity coefficient will decrease. That is, when the ionic strength is increasing, there's more deviation. There's more deviation. Now, approaches 1 at low. When the ionic strength is low, right, if it's very low, that is in case of high dilution, then we approach 1. So the closer you are to 1, the more ideal that you are. Very simple. Very simple. Right. Now we come to the extended Debye-Hackles equation. The extended Debye-Hackles equation. Now, the long and short of this equation is that it helps us to determine the activity coefficient from the ionic strength. Right? There are two ways of stating this equation. The first way is what has been shown here. Right? The first way is what has been shown here. Right? Good. Now, in this equation, we have log of the activity coefficient being equal to negative 0.51. This is the charge squared and the square root of the ionic strength all over 1 plus. And this is the ionic size. Now, the ionic size is actually a diameter. So let's look at this picture to understand it well. Now, from the center here to this side becomes what we call the ionic radii, right? Now, from this side becomes the hydrated radii. Now, if you add these two radius, right? So this is one radius, this is one radius. When we add these two radius, the radii becomes a diameter, right? So that becomes the alpha, right? So when we talk about the alpha, we are talking about the ion size, and the alpha is the diameter of the hydrated ion, not the isolated ion, but the hydrated ion, right? Good. So that is why we have picked this figure, not this one. Good. Now, for one of the most important things you have to notice about this is that the ion size here for this equation is measured in picometers. Picometers. Let's take note of this. And so always, when you're using this equation, you have to measure your ion in picometers for your calculation to be very simple. Now, we are also saying that the equation is valid when the concentration is less than or equal to 0.1 molar. Right, very important to note. Now, this is a table showing you the activity coefficient of some ions, right? Of some ions. We can notice some trends in this table, and we don't have to choose anything, right? So we have the ions here, we have the ion size here, and then we have the ionic strength here, right? If you take the first one like this, if you take just the first one, you realize that the concentration, the ionic strength is increasing. Now, when the ionic strength is increasing, you realize that the value here is decreasing. That is, once the ionic strength increases, the deviation from the ideal property or ideal solution also increases. So this one shows progressive deviation, right? The deviation is strongest at this point because the ionic strength is higher, right? Now, that is one of them. We can also check the size. Now, all of them have the same charge. Once the ionic size, that is the hydrated ionic size increases, you realize that there's a decrease. There's a decrease in the activity. That shows that there's more deviation with larger size, right? Once the size is increasing, the deviation becomes higher. So that's another thing that we can note, another trend that we can notice. Now we can also compare the different charges, +1, +2, and then let's say +3. Now for the same size, 800 here and then 800 here, you realize that the +1, right? The +1 is giving you 0.9. The plus 2 is giving you 0.8. So when the charge is higher, right, the deviation is more. That's one thing that we can also notice, right? That's the idea is that once the charge is higher, there's higher shielding, right? There's higher shielding. And so you realize that the deviation from the ideal solution is higher, right? That is giving us the lower activity coefficient. So these are random trends that we can notice from this table. Now, the next one is giving us a different way of stating the Haeckel equation, right? Now, the position of the negative sign doesn't make a difference. If it's here or it's here, it's the same thing as maths, right? So it doesn't change anything. Now, we still have negative log of the coefficient being equal to 0.1, 0.51, the charge squared, square root of the ionic strength divided by 1 plus 3.3. This is the ionic size, and then this is the ionic strength. Very important to note. Now, we are seeing that the equation is valid when the concentration is less than 0.1 molar, as we talked about for the other equation too. Now we are saying it is also valid when or it's applicable when the temperature used in the study was 25 degrees Celsius, right? Very important. Now everything is the same. The only thing I want us to note here is this one, that if we are using this equation, right, our life becomes very easy if our ionic size is measured in nanometers. Nanometers, not picometer. The other one was picometer. This one is nanometer. So this one will make our life very easy, right? And so if the question comes and then the alpha, right? The alpha, which stands for the ionic size, has been given in nanometer, it is very easy for you to use this formula instead, right? If it has been given in picometer, then you use the other formula, right? Good. But then if you want to keep one of the formula, there's a way we can convert picometer to nanometer. And the conversion is 1,000 picometer is equal to 1 nanometer. So 1,000 picometers is equal to 1 nanometer. That is that. There's a table showing how the nanometer thing also works. The values will be the same, right? Very simple. Very simple. Calculation. More calculation. Right. So what is the activity coefficient of magnesium ion in a 3.3 millimolar solution of magnesium nitrate using both equations? Right. So now they have asked us to calculate the activity coefficient, right? Now, before we get the activity coefficient, we have to get the ionic strength. The ionic strength. So we can calculate the ionic strength of the magnesium nitrate. The equation will be Mg bracket NO3 subscript 2, dissociating to give me Mg2 plus Mg2 plus 2 of the nitrate ions, right? Good. And so that is what we have here. Now the concentration here is 3.3 milli, right? Millimolar. This one will still be 3.3 millimolar, but this one will be 2 times 3.3 millimolar, right? So that will give me like 6.6 millimolar, right? So that is what we have here, the 6.6 times -1 all squared. This is the 2, right? So the plus 2 squared, you have 3.3 there. So we will calculate and then get this to be our ionic strength, but in order to standardize our calculation, we'll change it to molar, right? So the millimolar, the milli is times 10 raised to the power -3. So now we've converted it to molar, and that is the ionic strength that we have here. Now, after that, this is the first way of stating the equation. That's the log of the activity coefficient is equal to -0.15 times the charge squared times the square root of the ionic strength, which has been shown here, all divided by the 1 plus the 800. Now, this is the alpha, right? This is the ionic side. This is the ionic size. And so you realize that This one has been stated in picometers, right? The size here has been stated in picometers, multiplied by the square root of the ionic strength divided by 305. And then we'll get this number. Very simple. Now, the next equation, the same thing, right? The only difference will be if we are using the second equation, we have to make sure that this one is in nanometers. This one is in nanometers. And I said that before we can get to nanometers, we have to divide by 1,000. But 1,000 picometer is equal to 1 nanometer. If you are wondering where we got the 800 from, because it was not in the question, the 800 was gotten from this graph, right? So we have magnesium. Magnesium is here. Now in nanometers is 0.8. If you are looking at this table, magnesium is here. In picometers, it is what? 800. So that is where we got the value from. But in question in exams, they will give us the value to work with. And the truth is, if you use both equations, you are supposed to get the same answer, right? So you get the same answer. Good. Now, the exercise here, you are supposed to calculate the activity coefficient of 0.04 molar aqueous sodium phenobarbital at 25 degrees Celsius. Right? The 25 is important because we said when it's at 25, we can use the second equation, right? Which has been brought to ionic strength of 0.09 by adding of sodium chloride. Now we are seeing the mean effective ionic diameter of the phenobarbital, of sodium phenobarbital is this 0.2 nanometers. The nanometers has also given it away, so we'll use the second equation. It's a very simple calculation. We put in the figures. Yeah, so 0.1. The charge of sodium is 1. That is why I have not been showing you. So 1 squared is still 1. And then every other thing has been substituted well. And then when we punch it, we are supposed to get this as our answer. Very simple. Right. Now, the next exercise, very simple. We are supposed to calculate the ionic activity coefficient of 0.05 molar solution of HCl. Okay, so the question has given us the ionic activity coefficient. They are saying the ionic activity coefficient of 0.05 molar solution of HCl is 0.83 at 25. What is the pH? Now, pH, as we all know, is negative log. pH is equal to negative log of the concentration of H plus ions, right? Now, if it was an ideal solution, we would have had the CHL, HCl reacting to form H plus and then the Cl, right? Now, the biggest mistake we can make in ideal, that is in real solution, is consider that it is ideal. Now, meaning that we can just assume 0.05 molar here, this will be 0.05, this will be 0.05. But always when we give you the activity, you work with real solutions. When we give you the activity coefficient, you try and then you work with real solutions. So you find the activity, right? So you cannot just use the concentration here, you get it wrong. So what you have to do is that now, for you to get the actual concentration of the H plus ion, it would be the concentration here, the 0.05 times the 0.83, right? That will be concentration times the activity coefficient, and that will give you the effective concentration, also known as the activity, right? And that is what you use to find your pH. So if you look at the solution here, we have negative log of 0.83, which is the coefficient multiplied by the concentration. And this would result in your activity, which is the effective concentration, and that will give you a better pH value, right? Now, the next situation, same thing. We are saying that if sodium chloride is added to the HCl in the above to produce a total ionic strength of 0.5 for the mixture of the univalent electrode, right? The activity coefficient is 0.77. What is the pH? And so the same thing, instead of using the concentration, right? Just the concentration, you multiply the concentration by the activity coefficient so that you can get the activity. Then you find negative log of the activity to get you the concentration. That's it. And so in summary, we are saying the solution is, the ideal solution is one that is infinitely diluted. Most real solutions deviate widely from ideality. To simplify calculations, activity coefficient is often neglected, and molar coefficients, and molar concentration are applied in equilibrium. And the only reason is to simplify calculation, right? For some, the error introduced by the assumption of unity. Unity is 1. For the activity coefficient is not large enough to lead to false conclusion. However, the disregard of activity coefficient may introduce significant numerical error in calculation. Significant discrepancies occur when the ionic strength of a solution is larger than 0.01, when the ion involved have multiple charges, right? So when you have multiple charges being in play, then the ionic strength being more than 0.01, it means you have to consider the ionic activity, right? The activity coefficient. Now, for analytical chemistry, normally dilute solutions are used when concentrations become important to our calculation. We are using dilute solution to make sure that the solution we have is close to ideal as possible. Solubility equilibria. So this is a new concept, solubility equilibria, that we are introducing ourselves to. And when we talk about solubility, we are talking about the maximum amount of substance that dissolves in a given quantity of solvent at a given temperature. So the maximum amount of solute that will dissolve in a given amount of solvent at a given temperature is the solubility, right? Now, salts have extremely low solubility dissociates in water according to the principle. And so for conversation around solubility equilibrium, we will have to talk about reversible reaction. And then the reversible reaction will only come into play when we talk about sparingly soluble salt or salt with very low solubility. That is what we'll have this, right? Now, the normal equilibrium expression will be like this, but then this one is the solubility of the salt. And so we simplify the KSP, that is the solubility equilibrium constant, as this. So this is the expression for the solubility coefficient constant. The KSP is equal to the concentration of A raised to the coefficient of A multiplying the concentration of B raised to the appropriate stoichiometric ratio. That's the coefficient of what? B. So this is the formula for finding the KSP, right? Good. Now we are saying that solubility products deal with the equilibrium of sparingly soluble solids. I've already talked about it, right? Partially soluble solids, solubility of solids, and KSP expression. And so, the first question, I mean, we are supposed to, it's not as an example, to find or give an expression of KSP for silver chloride, right? Now, silver chloride is sparingly soluble. It will dissociate to give you silver ions and chloride ions. The KSP would be equal to the concentration of the silver raised to the power 1 and concentration of what? Chloride ion raised to the power 1. That is what we have here. If we are looking at magnesium hydroxide, this will be the dissociation equation. I would have concentration of magnesium raised to the power 1 and concentration of what? Hydroxide ion raised to the power 2, because the coefficient here is 2. And that will give us the KSP. Now, if we are looking at the bismuth sulfate, bismuth sulfite. Oh, okay. Bismuth sulfide. Yes. Sulfide, right? You're looking at the bismuth sulfide. The equation will be like this. Now, I would have the KSP being the concentration of bismuth raised to the power 2 and the concentration of sulfide raised to the power 3. Very important, right? So this is a table showing you some salts and then their KSP, right? Some solids and then their KSP. Now we have a question here to try. Let's try this question quickly. Now silver chloride will dissociate partially to give me Ag plus iodine minus. The KSP will be equal to concentration of Ag plus raised to the power 1 times concentration of I minus raised to the power 1. Now the lead iodide, right? Because of the subscript, you have to put 2 here so that it can be balanced. Now my KSP here would be equal to concentration of the Pb2 plus multiplying concentration of I minus raised to the power 2 because of the coefficient here. Very simple, right? So That is what we have down here. Now, we have to do some calculations. So they're asking us to calculate the solubility of calcium fluoride, right? They have given us the KSP. Now, we have to first of all write the dissociation equation for that. So partially soluble, we have calcium plus, 2 here, 2 of the fluoride ions, right? Now, at the initial part of the concentration, right, we would have 0 of these formed, right? But at equilibrium, we realize that if we have X most of this formed, if we have X most of this formed, we have 2X most of this one also formed, right? So that is what we'd have here for the equilibrium. Now, the KSP would be concentration of Ca2 plus concentration of fluoride ion raised to the power 2, right? Good. So that's it. Now, if I'm simplifying, the KSP value is 4.0 times 10 raised to the power -8 is equal to, now this one will be X. This one will be 2X raised to the power 2. And so if I simplify, I'm getting 4.0 times 10 raised to the power -8 is equal to, now this will give me 4X squared. If you multiply by this X, I'll get 4X cubed. S cube, right? So finally, my X would be equal to, that's mathematical, right? The cube root of 4.0 times 10 raised to the power -8 divided by 4, right? And the answer is here. The question has been solved here. So the answer will be 2.2 times 10 raised to the power -3 mole, and that is the solubility of calcium fluoride. There's another question for me to try. This one, they are giving me the solubility and they are asking me to calculate the KSP value. That's the constant. So copper bromide, CuBr, this is copper 1 bromide. The equation I would have I would have Cu plus Br minus, right? Now the KSP expression would be concentration of Cu plus concentration of Br minus, right? Now at equilibrium, if this is X mole, this is also X, right? So if this is X, this is X. And so the KSP value would be into bracket 2.0 times 10 raised to the power -4 multiplied by another 2.0 times 10 raised to the power -4, right? That is it. The solubility would be the X, right? So X is here, X here, it's just one more. So we just multiply the 2, and then we get our answer. It has been solved here, so very simple. We have 4 times 10 raised to the power -8 as our answer. Very simple, right? Now, the next question says we have to calculate the KSP value for bismuth sulfide, which has a solubility of 1.0 times 10 raised to the power -15 mole per liter. This is also a very simple question. We have bismuth, right? So Bi2S3. The equation I will get the bismuth 3 plus plus sulfide 2 minus. Now we have 3 moles of this, then we have 2 of this, right? So this is how the equation is. The KSP expression would be the concentration of Bi 3 plus all raised to the power 2 multiplying the concentration of this one all raised to the power 3, right? So that is it. If this is X, right, this will be 2X. So if this is X, this will be 2X. And then this will be 3X. So that is what we use in our calculation. So the KSP would be concentration of bismuth 2 times the X. This is the solubility, 1.0 times 10 raised to the power negative 15 all squared, multiplying 3 times x, which is 1.0 times 10 raised to the power negative 15 all raised to the power 3. Then we can simplify this to get our answer. This is what has been provided. We'll simplify, and then we'll get 1.1 times 10 raised to the power negative 73 as our answer. Very simple. Now we have another question to consider, another very simple question. We have given us the KSP, the case value of copper 2 iodates. Copper 2 iodates is 1.4 times 10 raised to the power negative 7 at 25. Now we have to find the solubility. Very simple question we can do without thinking. So the copper 2 iodates, like this, back and forth, right? Reversible reaction. We have copper 2 ions plus iodate ions minus. Now there are 2 of the iodate ions here, right? Now if at equilibrium, if we have x of this dissociating, we'll get x of this, and then 2x of this, right? Let me clean this because this is not a better comparison. So if we form x of this, we form 2x of this, right? That is the actual comparison I can. At this amount will be the initial amount minus, so we don't have to bring that one. So this is what I'll get, right? If I'm forming x of the copper, I'm forming 2x of this one. Now my KSP expression would be equal to the concentration of copper 2 ions raised to the power 1 times the concentration of iodates ions raised to the power 2, right? Now they have given us the KSP value, so we can put it there. 1.4 times 10 raised to the power negative 7 is equal to, now the copper concentration is x, right? The iodate concentration is 2x raised to the power 2. And so I have 1.4 times 10 raised to the power negative 7 is equal to, now this one will give me 4x squared, multiplied by this, I'll get 4x cubed, right? If I'm supposed to do change of subjects, I'll get x is equal to cube root of 1.4 times 10 raised to the power negative 7 all over 4, right? And that should give me my answer. If you follow the same suit, you come and get your answer as we have here. 3.3 times 10 raised to the power negative 3 mole per liter. That is that for that. Now, another simple question for us to practice: the molar solubility of silver sulfate in pure water is 1.2 times 10 raised to the power negative 5 molar. Calculate the KSP. Right, first of all, we have to write the equation. I'll get silver plus, that is 2 moles of silver, plus sulfate, it is 2 minus. Now, if this is x, this one is 2x, right? 2x because of the 2 there. And the KSP value, the KSP equation will be the concentration of the silver raised to the power 2 multiplied by the concentration of sulfate, right? Now, the KSP value would be equal to, now the silver would be 2 times x, which is this solubility they have given. The x is this solubility, always the x is the solubility. So I'll get 2 times 1.2 times 10 raised to the power negative 5, all raised to the power 2. We have to follow this calculation meticulously. And this is x multiplied by 1.2 times 10 raised to the power negative 5, right? And then when you solve, you are supposed to get your answer. The answer we are supposed to get from this one is 6.9. We have to get 6.9 times 10 raised to the power negative 15. Right. Common ion effects. And so common ion effects is a new concept that we are talking about, but it applies to solubility, right? Now, the name itself gives it away, common ion. And so if there's a solution, let's say containing chlorine, and then you add, let's say, sodium chloride, because sodium chloride will contribute chlorine to a solution which is already containing chlorine, we call the chlorine coming in a common ion. Now, it's a common ion because the solution already contains chlorine. So if I have a solution containing chlorine and I add any other solutes that has chlorine in it, it means I am introducing a common ion. And then the introduction of the common ion will bring an effect that we call the common ion effect. The common ion effect. So let's talk about the common ion effect. So they are saying it reads, an ion added to a solution already containing that ion is called a common ion. The common ion is when an ion common to one of the salt's ions is introduced to the solution. The introduction of a common ion produces an effect on equilibrium, right? Now, this effect is very simple. Let me use this to explain. Now, the solution, the equation here is silver chloride at equilibrium with silver ions and then chloride ions, right? Now, at equilibrium, if I introduce more chlorine ions, right, into the medium, according to Le Chatelier's principle, it says that in equilibrium, if there's any shift, right, if anything is added to the equilibrium has to shift in a way to cancel out that effect. And so what will happen here is that if I add more chlorine, it means the chlorine concentration has increased. Now the equilibrium will have to shift to my left, such that the silver here and the chlorine here will combine to reduce the amount of chlorine that has been added, so that equilibrium can be maintained. Let me repeat it again. Now, in this equation, the reversible equation, equilibrium has been established between silver chloride and its ions, right? Should I introduce a chloride ion into the medium, right? The chloride ion would increase the concentration of these chloride ion drastically. Now, for the equilibrium to be maintained according to Le Chatelier, the equilibrium should shift to cancel out that effect. And so the shifting. Now, in order to reduce the increased chloride, right, the equilibrium will shift to the left. It will shift to the left so that more of the Ag and then the chloride ions can combine to form the Ag chloride, so that the chloride ion can reduce to balance the one that has been added. This is what we call the common ion effect. Now, what is actually happening here is that in an attempt to reduce the number of chloride, which has increased all of a sudden, when the Ag combine, it forms the solid. And so more of the solid silver chloride will precipitate. And so the introduction of the chloride ion has decreased the solubility of the silver chloride. And that is what we call the common ion effect. So by introducing the common ion, the solubility of the sparingly soluble salt has decreased because of shifting equilibrium. Common ion effect. Now, if there's any mechanism in the medium that consumes or probably shields the chlorine, right? Shields the chlorine in order to maintain the number of chloride ions present, the equilibrium will shift towards the right so that the chlorine level can also increase. So that is the balance. That's why Le Chatelier said, right? So let me read again. They are saying that introduction of a common ion produce an effect on the equilibrium of the solution. Now, according to Le Chatelier principle, that is the equilibrium is shifted so as to reduce the effect of the added ion. This is referred to as a common ion effect. Example is silver. Example is when silver nitrate is added to a saturated solution of silver chloride. Now, in this example, they are adding silver nitrate. So the silver nitrate would completely dissociate and introduce more silver ions, right? Yes, now the equilibrium has to shift to the left due to the increased silver ions. And as a result, the chloride and then the AgCl solubility will decrease. The AgCl and the AgNO3 have a common ion, which is the Ag. A shift in the equilibrium position upon addition of an already contained ion in the solution is known as the common ion effect. A salt will be less soluble if one of its constituent ion is already present in the solution. So that's all about common ion effect. Now we can apply the knowledge of common ion effect in calculation. So, and this will actually help us understand the concept better. So let's solve this question. The KSP value, you've solved a lot of these questions, so I wouldn't really worry myself. And they have given us the KSP value and they asked us to find the solubility. This will be the equation for the dissociation equilibrium equation. This will be the expression for the KSP. Now, if this is X, right? So very simple. The KSP value has been given. This one will give me S squared. So when you find the square root of this, you're supposed to get your solubility. So very simple. And that is what has been found here, 1.3 times 10 raised to the power negative 5. If I'm supposed to go over the calculation, once I get my KSP, if this is X, right? So my KSP, taking it from here, would be equal to x multiplying x raised to the power 1 raised to the power 1. So I'll get 1.7 times 10 raised to the power negative 10 is equal to x squared. So we just find the square root of this, the square root of this side. You get x is equal to 1.3 times 10 raised to the power negative 5. So that is it, right? That's it. That's the solubility. That's the solubility. That's it. Now, the next question. This is when the common ion effect comes in. So this one, I would have to take my time and explain it very well. Good. So what will be the remaining chloride ions in solution when silver nitrate is added to a saturated silver chloride solution until the Ag plus is 0.10? So now what they are saying, let me rewrite the equation. AgCl reversibly breaking into Ag plus Cl minus, right? Now they are saying what will be the remaining Cl concentration, so the solubility anyways, in solution when silver nitrate is added. So now we are adding silver nitrate, right, to a saturated solution of the AgCl solution until the concentration of the silver ion is 0.1. So they have given us the concentration of the silver ion to be 0.1, right? Now the KSP here will still be constant. The KSP will not change. The KSP change with change in temperature, not change in concentration. So the KSP expression will still be silver multiplied by the concentration of this, right? Now they have given us the KSP, right, which is 1.7 times 10 raised to the power negative 10, right? Now they have given us the concentration of the silver now, which is 0.1. Now we don't know the concentration of the Cl minus. So this is what we have. We divide this by 0.1, divide this by 0.1, and that should give us our answer. Right, that should give us our answer. So our answer is 1.7 times 10 raised to the power negative 9 mole per liter. Very simple. Very simple. Good. Another question for us to try. Calculate the solubility of calcium fluoride. Yes, they have given us the KSP in a solution of 0.025 molar NaF solution. So this one, very simple. We've already done calculations around the fluoride, but let me go over this calculation for us. The calcium fluoride will break down to form calcium ion plus 2 of the fluoride ions, right? Calcium ion plus 2 of the fluoride ions. Now, the sodium fluoride will dissolve completely to give me sodium ions plus fluoride ions. The sodium ions will not be necessary in the common ion effect calculation because it has no common ion here, but the fluoride is here. So if it's complete dissociation, 0.025 would give me 0.025 here, right? So this is the contribution of fluoride ion coming from here. Now at equilibrium, if I get X of this, I get 2x of this, right? But then this salt alone, the sodium fluoride is adding an extra 0.025. So the total fluoride would be 2x plus 0.025. Now the KSP expression will be very simple, same as we have been doing. Concentration of calcium, concentration of fluoride, raised to the power 2, right? Now, the KSP, the KSP value has been given. Let me just repeat KSP here. Now, the calcium here would be X, right? Then the fluoride here will be 2x plus 0.025, right? Now, there's an assumption that we do here. The assumption is that the solubility is very small compared to this number. So when you add the solubility plus this number, approximately, you still get the same number here. So we say that the 2x plus 0.025 is approximately 0.025 because the x is a very small number compared to the concentration here. And so the KSP will now be simplified to x multiplying 0.025, right? Now the KSP has been given in the question. It's 4.0 times 10 raised to the power negative 11. Now it's equal to x times 0.025. You divide this side by 0.025, this side by 0.025, and then that should give us our answer. That should give our answer. And our answer is 6.4 times 10 raised to the power negative 8 molar. Another simple question for us to try. So many simple questions coming. Now we are saying that the mineral barytes, which is mostly barium sulfides, and is widely used in the industry and in medical imaging of digestive system. Calculate the molar solubility at 25 degrees Celsius of barium sulfate in A, pure water, B, salt water, in which the concentration of sulfate ion. Now, sulfate ion is being mentioned because a common ion when you talk about the barium sulfide is 2.8 gram per liter. Now, this particular question will borrow some knowledge from chemistry that you know. So if you don't have that knowledge, you might find the second question quite challenging. You just need to borrow some knowledge. So I will lend you all the knowledge today. Now, the first question is actually a very straightforward question. It's in pure water. There's no common ion, right? The equation for barium sulfate is this. Ba2 plus sulfate 2 minus, right? The KSP expression would be concentration of Ba2 plus and then sulfate 2 minus, all raised to the power 1. So we don't have a problem with that. Now in pure water, 9.1 times 10 raised to the power negative 11 is equal to, if this is x, this is x. So I would have x times x, right? So I have 9.1 times 10 raised to the power negative 11 is equal to x squared. You find square root of this side, square root of this side, and that should give you the answer in pure water, right? So my answer would be 9.5 times 10 raised to the power negative 6 molar. Very simple. Now in seawater, the first thing we have to do is that always our calculation is molar. We are calculating molar solubility. But this one has been given to us mass density. So that's the first thing we have to do. We have to convert the mass density to what? To molar. Now there's this formula which is P is equal to MC. The P here is the mass density, the M here is the molar mass, and the C is the concentration, which we want. And so if you are making C the subject, C will be equal to P over M, right? That is for us to convert the mass density to concentration, we have to divide by the molar mass, right? But now the mass density has been given as 2.8. 2.8. The molar mass of sulfate ion. Sulfate, just sulfate, because this is for sulfate, right? Sulfate. Now sulfur is 32, atomic number 32. Mass number 32. And then oxygen is 4. Oxygen is 16, right? Oxygen is 16. If you look at SO4, there's 4 atoms of oxygen. So would have 4 multiplying 16 plus 32, and that should give me 96. So if you do the calculation, you get 96. But appropriately, it's 96.06. But you can use the 96 for your calculation, right? So 96.06. And that should give me my concentration. That should give me my concentration, right? Yes, that should give me the concentration is this one, concentration is 0.029. That's when you do the division. That is what you get. Very simple. Very simple. Now, we come back to our conversation. The equation for the KSP, same thing, right? Concentration of barium 2 plus multiplying concentration of sulfate minus iron, right? Now, if this is X, according to the concentration, if this is X, this is supposed to also be X. But then because of the contribution from the seawater, right, this molar of sulfate will have to be added. So the sulfate now will become, the total sulfate will become 0.029 plus the X coming from the dissociation of the salts, right? So if I'm using my KSP is equal to barium, which is X, and then the sulfate, which is now X plus 0.029. 0.029 is coming from the sea, right? It's coming from the sea water. Now, just as we made the assumption in the first place, the x plus 0.029, the x is very small compared to the 0.029. So approximately the x plus 0.029 here will be approximately equal to the 0.029. So we just ignore the x. So my KSP will be equal to x into bracket 0.029. Divide this side by 0.029. This side by, that's the KSP by 0.029. Sorry. The KSP by 0.029, and that should give us our answer. Right, that should be our answer. And our answer is 3.1. It's 3.1 times 10 raised to the power negative 9 molar. Some simple questions for us to consider. What is common ion effect and how does it affect solubility? We've talked about that, right? What's a common ion? Common ion is an ion which is introduced to a solution already containing that ion. That's a common ion. And then when you introduce a common ion, it decreases the solubility. Right? Decrease the solubility. So that is just a very simple. Now the next question said a beaker contains a saturated solution of calcium chloride. Right? KSP 4 times 10 raised to the power 11. There are some sodium ions in the solution. If sodium fluoride is added to the beaker, which of the following will occur? Now, the first one is the concentration of sodium will decrease. That is false. I mean, if you're adding sodium fluoride, the concentration of sodium will never decrease. It would actually increase. So the next question, and the next option is the concentration of calcium will decrease. Now, that is something which can be true because we have calcium fluoride at equilibrium, right? So we have calcium 2 plus 2 of fluoride ions. Now, if I add the NaF, right, it would introduce more fluoride ions. Now, when the fluoride ion concentration is increased, in order to restore the balance according to Le Chatelier, the equilibrium will shift backwards. That will allow more of the fluoride and the calcium to combine to form this. Right? So as the fluoride and calcium are combining to form this, the concentration of calcium is what decreasing. So this is correct. Now the concentration of fluoride, the concentration of F would decrease. That is not true. Actually, it would increase and the balance would occur to restore it. All concentration will remain constant. That's also false, right? So the answer would be B. Very important. Now we have some questions to try. These questions are tagged midterm questions. Now what you have to know is that they are likely examination questions, right? The first one is that explain the leveling effect of water using the reaction of HCl and then HCl O4 with water as example. Now the leveling effect has already been explained. When you add every strong acid to water, it reacts to give you hydrozonium ion, and hydrozonium ion is the strongest acid that can exist in water. If you add every base, any strong base to water, it would give you hydroxide ion, and hydroxide ion is the strongest base that can exist in water. So all strong acids are leveled to hydrozonium ion. All strong bases are leveled to hydroxide ions. Very simple, right? That's the equation to explain. Now, find the pH of this solution. This is a very simple calculation. Because it's ammonia, yeah, you can find the pOH first and then probably use the pOH to find the pH. Let me take us through the calculation quickly. So first of all, we have written the equation for how ammonia will interact with water. Now the Kb expression will now be written, right? Water is a pure liquid and it's not added to the Kb expression. This is the Kb expression. Now, if this is X, this will be X. This one has been explained so many times, right? If this is X, this will be X. And then the amount of this at equilibrium will be the initial amount, 1.5 minus X. Right, so that's it. But the truth is that X here is very small. So if I have 1.5 minus X, it will still be approximately 1.5. Approximately 1.5. That is why we have the 1.5 here. Right? Good. So we substitute them here. And then we do our mathematical evaluation, and then we'll come and get the value of X. The value of X is the concentration of the ammonium ion and the hydroxide ion here. Right. Once we get the concentration of the hydroxide ion, we can decide to find the negative log of the hydroxide ion to get our pOH. A negative log of the hydroxide ion to get our pOH. Then we subtract the pH from 14 to get the pH, right? That's one way, but that's not the way that was used here. In this one, they use this, the Kw, that's the ionic product of water, is equal to concentration of H plus multiplied by the concentration of H minus ion. So they made the H plus the subject and then found the concentration of the H plus, then found negative log of the concentration of H plus to get the pH. Very simple calculation. Very simple calculation. Yes, the second one that just came here is what I was talking about, the pH, right? So this one, they found the pH, subtracted from 14 to get the pH. Very simple. Now, another simple question. We are supposed to calculate the ionic strength, right? The ionic strength. Now, if you remember the short form that we use, we can check whether it is true here. Now, this is +1 minus 2. That's the charge. So this is 1:2. And then we said if it's 1:2, there is 3 times. It's 3 times the concentration. You can quickly go and look at the answer and realize that the ionic strength is 3 times the concentration here. But we can also go through the calculation and then we'll get the answer. That's so we have come to the end of the discussion on whatever we had to discuss in the previous slide. Now, the last part of the video would talk about the electrolytic conductance and then resistance, right? And so that will be captured in part 4. Thank you very much. If you have any issue, kindly see any member of the HESA Academic Board. Thank you so much and have a nice day.